There's a disquieting theory that offers an explanation for why the universe is so quiet, suggesting it is a dark forest teeming with unseen predators. Within this cosmic wilderness, the cardinal rule for survival is silence, as any being that exposes itself is likely to be swiftly eliminated by a more powerful force. Imagine that one day, while gazing into this silent expanse, you spot a subtle clue, not a sound or the flicker of a distant flame, but the equivalent of a single broken twig, a faint, almost unnoticeable sign that something passed incredibly close by. In 2017, we witnessed the first such sign, the perplexing object known as Oumuamua, which traveled in a way that seemed to disregard the laws of physics. Following that was a second visitor, a standard comet whose predictable behavior was, by contrast, quite reassuring. But now, a third wanderer has made its way into our cosmic neighborhood, and this time, the circumstances are entirely different. Its path appears unnervingly precise, and its actions are highly unusual, creating a chain of improbabilities that compels us to consider a chilling question. What if we are no longer dealing with an accidental traveler? Could this be more than just a random passage in the dark, but instead a purposeful arrival? An object, catalogued as 3I/C, is currently on a course toward us, navigating as if it possesses a map of our solar system more detailed than our own. It seems to be strategically using the gravitational pull of our planets, executing a complex celestial maneuver that could allow it to stay in our system indefinitely. Are we witnessing a spectacular cosmic fluke? Or is this the result of a cold, alien intelligence at work? Let's temporarily set aside our preconceived notions about visitors from other stars and carefully observe this silent newcomer. It is, at this very moment, composing a new chapter in the saga of humanity, and it falls to us to uncover the identity of its true author. Major breakthroughs in contemporary astronomy seldom start with a dramatic cry of Eureka. In fact, they almost never happen in the dead of night as a solitary astronomer looking through the lens of a massive telescope suddenly discovers a new celestial body. The modern frontier of knowledge has migrated elsewhere. Today, the real work takes place in the climate-controlled hum of server rooms, where sophisticated algorithms relentlessly analyze terabytes of data collected by robotic observatories. A discovery no longer starts with a person's exclamation, but with a quiet line of computer code appearing on a screen. It's a digital flag, raised by software that has identified an anomaly, a minuscule point of light behaving in a way that defies all known patterns. This is precisely how our current mystery emerged from the digital ether. Picture a global network of telescopes stretching from Hawaii to South Africa, named Atlas in a nod to the mythological Titan who held up the heavens. The name, however, is an acronym with a much more practical and sobering purpose: the Asteroid Terrestrial Impact Last Alert System. Its chief function isn't to expand our philosophical horizons, but to serve as a line of defense. Every clear night, these automated telescopes systematically survey the observable sky, capturing images of one sector, then the next, and then returning later to photograph those same areas again. From there, specialized software assumes control. It overlays the latest image on top of the previous one, and, like a diligent proofreader, removes everything that is unchanged. It confirms that one star is still in its place, as is another, and that a particular nebula has not shifted. But then it spots something new, a tiny, faint speck of light that either wasn't there before or has changed its position. This becomes the system's focus. Usually, this turns out to be a known asteroid, following its well-documented orbit, or, occasionally, a newly found object native to our solar system. The program flags it, computes a preliminary trajectory, and adds it to a database, all part of the routine work of charting our celestial surroundings. On July 1st, 2025, the system performed its duty just as it had for thousands of nights. It logged another dim, moving point that initially seemed unremarkable. However, when the initial orbital calculations were processed, the results were jarring. The computer generated a trajectory so unusual that it prompted the astronomers on duty to take a much closer look. The path of this object was profoundly strange, even impossible for anything originating within our solar system. To grasp just how impossible its trajectory was, a quick lesson in celestial mechanics is in order. Imagine you are on a very tall mountain, throwing stones. A gentle toss sends the stone on a short arc before it falls to the ground, a closed path. If the planet weren't in the way, that stone would continue in an elongated circle around the planet's center, known as an ellipse. This is the way all planets, comets, and asteroids in our solar system move, bound by the sun's gravity since their formation, lacking the initial force to ever break free. Now, picture yourself as a figure from myth, strong enough to hurl a stone with such incredible power that it escapes the planet's gravitational pull and flies off into deep space, never to be seen again. The velocity needed to achieve this is known as escape velocity, and the stone's path would no longer be a closed ellipse, but an open curve that mathematicians define as a parabola, the trajectory of departure. But there is a third, entirely different scenario to consider. Imagine the stone was never thrown by you at all. Instead, it arrives from the vastness of interstellar space, already moving at an immense speed. It streaks through your planet's gravitational field, its course only slightly altered by the pull, before disappearing back into the void. Its velocity is so extreme that gravity cannot capture it or even substantially slow it down. This path is also an open curve, but one even sharper than a parabola, a hyperbola. The calculations for this new object revealed exactly such a hyperbolic trajectory, serving as undeniable proof, like a passport from another star, that this visitor was not from our home system. This object did not originate with Earth, Mars, and Jupiter from the same swirling cloud of gas and dust some 4.5 billion years ago. It was an interloper, a foreigner, an alien in the truest sense of the word. In astronomy, a parameter known as eccentricity is used to define the shape of an orbit. A perfect circle has an eccentricity of 0, while the elliptical paths of planets have a value slightly above 0, but always under 1. An object on a parabolic escape path has an eccentricity of exactly 1. The value for the body found by the Atlas system was substantially greater than 1. This indicated that the object was not simply breaking free from the sun's gravity. It had stormed into our system with so much surplus velocity that our star was merely a temporary gravitational hurdle. It was an obstacle the object would easily surmount and leave behind without a second thought. Its speed relative to the sun measured in the tens of kilometers per second, vastly outstripping the escape velocity at any point from our star. Once other observatories verified the finding, the object was given its official designation, 3I/Atlas. While Atlas acknowledges the system that found it, the 3I portion is what holds the real significance. The I signifies that it is interstellar, meaning its origins lie far beyond our solar system. The number 3 reveals that this is only the third confirmed object of its kind in the history of observation, the third traveler from outside our celestial home. You might initially wonder what makes this so extraordinary. Space is immense, with stars constantly being born and dying, and planetary systems forming and breaking apart. It stands to reason that interstellar space would be teeming with countless castaways, comets and asteroids flung from their native systems by gravitational disturbances. The fact that we've started to detect these wanderers could simply be a testament to the growing power of our telescopes. We're finally able to see what has always been there, just beyond our view. This perspective is logical and would be entirely correct, were it not for a few critical details. And in this story, as with any good detective novel, the truth is hidden in those very details. The first element that sparked suspicion was the discovery itself. With only 3 such objects found, 2 years separated the first and second, while 6 years passed between the second and third. While the data is too limited for firm conclusions, it implies that these are incredibly rare occurrences. Every visitor represents a singular chance to peer beyond our own world and analyze a piece of another star system, making each one worthy of our most intense scrutiny. And as soon as that scrutiny was turned on Object 3, it began to unveil a series of enigmas. The first puzzle concerned where and how it chose to announce its arrival. This wasn't just another faint dot on a star chart. It was a distinct signal, emanating from the cold, silent frontier of our solar system. This signal was far too strong, arrived far too early, and was utterly inexplicable based on our existing knowledge of such celestial bodies. So, what was it? Was it just a common interstellar nomad with an unusual yet natural set of properties? Or was it something more? We are at the very beginning of this journey, having just received the first dispatch from this stranger, written in a language we have not yet learned to read. The investigation is just getting underway, and the first order of business is to meticulously survey the scene of the event, that remote, frozen region of space where this visitor first revealed itself. It is in that location that the initial and perhaps most vital clue in this cosmic mystery is concealed. To grasp just how bizarre the first appearance of Object 3I was, you need to imagine the solar system not as a series of circles in a textbook diagram, but as a vast, climatic map. At its heart burns the incredible furnace of the sun. As you travel outward, intense heat fades to warmth, which then gives way to coolness, followed by an eternal and unforgiving cold. Each planet follows its orbit within a distinct climatic zone. Mercury is a scorched wasteland, while Earth is a precious oasis where liquid water can exist. Mars presents a frozen tundra. Past the asteroid belt, you enter the domain of ice, home to Jupiter, Saturn, Uranus, and Neptune, ice giants orbited by frozen moons. Here, temperatures plunge to -150 to 200 degrees Celsius, and ordinary water ice becomes as hard as granite, no longer melting or evaporating. The sun's rays, weakened over their journey of hundreds of millions of kilometers, are too feeble to even melt frost from a cosmic body's surface. This unseen boundary, beyond which water is locked in a permanent deep freeze, is known in astronomy as the snow line or frost line. And it was out beyond this line, in the icy wilderness near Jupiter's orbit, and even slightly farther out, that our guest was first detected. This in itself isn't what's astonishing, as our telescopes can see objects at much greater distances. The surprise was in how they saw it. It wasn't merely a dim speck of reflected sunlight, which is what you would expect from a typical asteroid or a frozen comet. Instead, the object was already showing signs of activity. It was enveloped by a faint but discernible gaseous cloud, a temporary, thin atmosphere that astronomers refer to as a coma. It had already begun to stir into life, and this was the genuine anomaly. Let's be clear about what a comet is. It is, in essence, what astronomer Fred Whipple famously called a dirty snowball. A comet's nucleus is a composite of water ice and frozen gases like carbon dioxide, methane, and ammonia, all intermingled with dust and rock. As long as a comet remains in the distant, frozen reaches of space, it lies dormant and is practically indistinguishable from an asteroid, nothing more than a lump of soiled ice. However, as its orbit carries it inward toward the Sun and it crosses the snow line, a remarkable transformation starts to occur. The escalating solar heat begins to warm the nucleus's surface. In the vacuum of space, the ice doesn't melt but sublimates, changing directly from a solid into a gas. This process causes jets of gas and dust to erupt from the surface, creating countless miniature geysers that shroud the nucleus in a dense cloud, the coma, which can expand to be larger than the planet Jupiter. Solar radiation pressure, combined with the stream of charged particles from the Sun, known as the solar wind, acts upon the material of the coma. This force extends the matter outward, forming two stunning tails. One, a straight, bluish trail of gas, and the other, a curved, yellowish stream of dust. The awakening of the comet is a process that hinges entirely on temperature. For water ice to transition directly into gas, a specific thermal threshold must be met, a point typically reached much closer to the Sun, somewhere between the orbits of Mars and Jupiter. However, this object, designated 3I/c, was detected far beyond Jupiter's orbit, in a region still profoundly cold. In that frigid expanse, water ice should have remained completely solid and inert, yet the object was unmistakably active. How could this be? The most straightforward explanation is that the comet's nucleus isn't made of ordinary water ice, but rather of far more volatile materials. The cosmos contains other types of ice, such as frozen carbon dioxide, also known as dry ice, and carbon monoxide, which turn to gas at significantly lower temperatures. A comet with a high concentration of these substances could certainly become active at such an extreme distance from the Sun. This is a completely valid scientific hypothesis, as comets within our own solar system contain these materials, though typically in minor quantities. It's possible this interstellar visitor originated in a much colder environment, where these volatile gases were the main components for its formation, giving it a unique chemical signature that would be incredibly fascinating to analyze. Yet, this theory immediately presents another challenge. If the object is outgassing so vigorously at such a great distance, its nucleus must be truly enormous. The coma, we can see, is a direct product of this sublimation. A larger coma implies a greater volume of vaporized material, which in turn requires a very large source. Initial calculations suggest that to generate such activity so far from the Sun, the comet's core would need to be tens of kilometers in diameter, ranking it among the largest comets ever documented. This brings us to a logical crossroads with two primary natural possibilities. The first option is that we are observing a giant comet composed of supervolatile ices whose immense size accounts for its early activity. While plausible, this would make the object extraordinarily rare, perhaps even one of a kind. The second option is that this is not a comet at all, but a solid, non-evaporating body like an asteroid. But if that were true, how could we even see it from so far away? An inert asteroid at that distance would have to be incredibly massive to reflect enough sunlight for our telescopes to detect it. According to calculations, its diameter would need to be around 20 kilometers, which again would classify it as a giant, far exceeding the size of most known asteroids. In either conventional scenario, we are faced with an object of exceptional scale, either a colossal, unusually active comet or a gigantic asteroid. This fact alone makes the discovery a matter of great fortune and deep curiosity. But a third possibility introduces an element of investigative intrigue. What if the feature we have identified as a coma or a tail is not real? A hypothesis advanced by Avi Loeb and his team proposes that it might simply be an optical artifact. Astronomical images require long exposure times, sometimes several minutes. A fast-moving object can change its position during this period, so if the telescope tracks the fixed stars, the object itself will be smeared into a short streak instead of appearing as a single point. If this moving object also has an irregular shape and is rotating, the resulting visual distortion can create the convincing illusion of an extended coma or tail, where none exists. This is an ingenious trick played by the very nature of observation. We are not seeing the object itself, but a two-dimensional projection warped by time, motion, and distance. Distinguishing a genuine coma from a photographic illusion at the edge of visibility is a profoundly difficult undertaking, demanding dozens of observations from multiple telescopes to construct an accurate model of the object's movement and rotation, and to eliminate any potential errors. So, you are left with three working theories. The first posits a giant comet with a unique chemical makeup. The second suggests a massive asteroid. And the third proposes a smaller body whose image has simply deceived us. Each of these explanations is compelling, yet none is conclusive. We find ourselves in the position of detectives studying peculiar tracks in a vast, snowy wilderness. They might belong to a very large known animal or to a smaller creature that left a distorted, blurry trail. Or perhaps they were not made by an animal at all. This fundamental uncertainty creates an opening for more audacious theories. When conventional explanations demand an escalating number of assumptions, that the object must be gigantic, its composition must be singular, and its appearance a remarkable coincidence, the temptation grows to look for an alternative. What if its unusual activity isn't sublimation? What if it's a controlled release of material? What if its size is an illusion, and its brightness stems from other factors? The puzzle of its premature activity is merely the opening chapter in its bizarre narrative. It confronts us with something that challenges our established models, forcing us to either stretch those frameworks to accommodate natural objects with unbelievable characteristics, or to consider that we may be witnessing something not entirely natural. This phantom that emerged from the icy depths has compelled us to take notice, and now, having captured our attention, it has started to unveil even stranger qualities, not in its appearance, but in the very fabric of its being, revealed in the geometry of its trajectory through our solar system. Before we delve further into the strange saga of Object 3I/C, it's essential to understand the person at the heart of the story. To grasp the scientific drama unfolding, you need to know the motivations of its central figure. Abraham Loeb, a Harvard astrophysics professor whom everyone calls Avi. While some hail him as a pioneer expanding the frontiers of science, others brand him a risky populist who chases headlines and weakens trust in the scientific method. So, the question remains, who is the real Avi Loeb? Looking past the sensationalism reveals a profile of a profoundly brilliant and prolific scientist, not an armchair theorist with outlandish ideas. Loeb is a well-established member of the scientific community, having previously chaired the astronomy department at Harvard, one of the most prestigious universities in the world. With hundreds of publications in premier journals covering topics from dark matter to black holes, his contributions to mainstream science are vast and indisputable. It is precisely because he is an insider who understands the system so intimately that his critiques resonate so powerfully and cause such discomfort. The central argument Loeb has advanced in recent years is that fundamental science today has grown overly cautious and risk-averse. He contends that scientists have effectively become a priestly class, content with solving safe, familiar puzzles within established paradigms. They shy away from proposing audacious, unproven hypotheses to protect their reputations, particularly when it comes to the intersection of science and philosophy, like the existence of extraterrestrial intelligence. This profound question has been largely abandoned to fiction writers and filmmakers, becoming a career-ending taboo within academic circles. In response, Loeb advocates for a new approach he calls space archaeology. He invites you to envision astronomers as archaeologists of the future, exploring the cosmos. An archaeologist digging up an ancient city wouldn't disregard a plastic bottle just because it seemed out of place. On the contrary, that very anomaly would represent the most significant find. In the same way, Loeb insists that astronomers must stop ignoring cosmic oddities, celestial objects that don't fit neatly into our current understanding, and instead study them with heightened focus, as they could conceal the most momentous discovery ever made. This guiding philosophy was the driving force behind his creation of the ambitious Galileo project. Named in honor of another famed scientific heretic, this initiative is dedicated to the systematic and rigorous search for technosignatures, any evidence of technology from beyond Earth. It's crucial to understand that this marks a significant departure from the traditional Search for Extraterrestrial Intelligence, or SETI, program, which has spent decades listening for radio signals. Loeb views that method as excessively passive and constrained, asking what happens if other civilizations don't use radio or simply have no desire to contact us. The Galileo project shifts the entire paradigm from listening to looking, prioritizing the search for physical artifacts over intercepted messages. These potential artifacts could range from operational or derelict spacecraft to automated probes investigating our solar system, or even tiny fragments of space debris left by alien activity. The project's objective is to establish a worldwide network of telescopes and sensors that will continuously scan the heavens for objects displaying abnormal traits, such as peculiar shapes or unnatural spectra. Should such an object be detected, it would be scrutinized with every available tool, ensuring the hypothesis of an artificial origin is not dismissed out of hand. It is precisely through this framework, the mindset of a space archaeologist, that Loeb examines every interstellar object that enters our solar system. Like a detective, he works with the same publicly available data as his peers, yet he arrives at a different interpretation. While his colleagues might identify a comet with strange characteristics, Loeb perceives a possible artifact masquerading as one. His approach involves hunting for anomalies that are difficult to explain through natural processes, and once several accumulate, he suggests that extraordinary objects demand extraordinary explanations. The response from the scientific community to Loeb's work has been decidedly polarized, to say the least. A significant number of scientists criticize him for drawing sweeping conclusions from sparse and often incomplete information, pointing out that plausible natural explanations exist for every anomaly he highlights. These critics contend that he inverts a core tenet of science, that extraordinary claims demand extraordinary evidence, by instead offering an extraordinary hypothesis built on little more than a handful of odd coincidences. He faces accusations of prioritizing fame over the quiet, diligent work of the formal scientific process. Conversely, Loeb also has a substantial number of supporters who view him as a revitalizing force in what they see as the stagnant atmosphere of academic science. They believe he is posing the right, albeit uncomfortable, questions, compelling scientists to venture beyond their intellectual comfort zones and confront possibilities they might otherwise ignore. His proponents often draw parallels between him and the great scientific dissenters of history, such as Copernicus, Galileo, and Darwin, whose revolutionary ideas were first met with fierce resistance for disrupting the accepted understanding of the world. Some have suggested that the non-terrestrial technology hypothesis could be the Copernican revolution of our century, though the reality is likely more nuanced. Avi Loeb is undeniably a catalyst in this conversation, a figure who sparks intense debate on subjects long deemed off-limits. While his specific theories about Oumuamua, or 3I/C, might ultimately be proven wrong, and these objects may just be exceptionally strange natural phenomena, his willingness to ask, "What if?" embodies the very spirit that drives scientific advancement. Therefore, when you hear the renowned astrophysicist Avi Loeb propose that we are looking at an alien spacecraft, it is essential to appreciate the complexity behind his statement. This isn't a declaration from the fringes. It is the calculated stance of a serious scientist, rooted in his distinct scientific philosophy. He effectively challenges his peers by demanding they prove him wrong, not by dismissing the anomalies individually, but by explaining them all with a single, coherent natural theory that accounts for all the peculiarities of these interstellar visitors. If they cannot, he argues, then his hypothesis, however extraordinary, deserves to be considered. This intellectual conflict between radical inquiry and scientific orthodoxy sets the stage for the entire saga of interstellar objects. And Loeb is far from a mere observer. He is an active participant whose own work helps define the research agenda itself. To grasp the foundation of his conviction, you must journey back to October of 2017, when a mysterious object shattered our scientific paradigms and fundamentally altered the conversation. It was a turning point that established a precedent for all subsequent debates. Its name, Oumuamua, which evokes the music of distant islands, translates from Hawaiian as scout or a messenger from afar arriving first, a title it unquestionably earned. Oumuamua was the very first object in astronomical history confirmed with absolute certainty to have originated from outside our solar system. Before its arrival, we could only theorize that such interstellar travelers existed. Afterward, we had proof. But its significance lay not just in being the first, but in being profoundly strange. So strange that years after its brief passage, there is still no scientific consensus on its true nature. Oumuamua's most famous oddity was its shape, which we were unfortunately unable to capture in a direct image because it was too small, too far, and moving too quickly. All our telescopes could see was a single point of light, but even that can be incredibly revealing if you meticulously track its changes in brightness. This technique, known as light curve analysis, allowed astronomers to infer its physical characteristics without seeing it directly. To understand how this works, picture yourself in a darkened room as an object flies by. If the object is a perfect sphere, its brightness will appear constant because it reflects the same amount of light regardless of how it spins. However, if it's shaped like a pencil, its orientation dramatically changes what you see. As it rotates, it will alternately show you its long side, reflecting a maximum amount of light, and its narrow end, reflecting a minimum, causing its brightness to pulse. By carefully studying the periodic swings in Oumuamua's brightness, which varied by a factor of 10, astronomers came to a startling conclusion. To account for such a dramatic fluctuation, the object had to possess an extremely elongated form, with a length-to-width ratio of at least 5:1, and perhaps as high as 10:1. This suggested a shape like a cigar or a needle, but subsequent analysis also indicated it could have been an incredibly thin, flat object, tumbling like a pancake through space. Either of these geometries is entirely atypical for any natural asteroid or comet we have ever observed. The combined forces of gravity and cosmic erosion tend to shape objects into more rounded or potato-like forms. Among the 1.5 million asteroids catalogued in our own solar system, none possess such radical proportions. Yet our very first confirmed interstellar visitor did. This startling fact, combined with the cigar-like shape's resemblance to spaceships in science fiction, was the initial anomaly that gave many scientists pause. But if its bizarre shape was merely surprising, a second anomaly presented a true scientific puzzle. As astronomers tracked Oumuamua's path with extreme precision after it rounded the Sun, they discovered that it was not following the trajectory dictated by gravity alone. The object was accelerating away from the Sun with a small but undeniably measurable extra push, defying the classical laws of celestial mechanics. In essence, it was moving slightly faster than it should have been, if only the Sun's gravitational pull was influencing it, as if some other force were propelling it forward. The most common explanation for this is the effect of cometary outgassing. As a comet is heated by the Sun, jets of gas and dust erupt from its surface, creating a reactive force that acts like a small engine and produces what is known as non-gravitational acceleration, a well-documented phenomenon. However, this theory presented a massive problem when applied to Oumuamua. The amount of outgassing required to generate the observed acceleration would have produced a substantial coma or tail of dust and gas. Yet, despite being scrutinized by our most sensitive instruments, including the Spitzer Space Telescope, Oumuamua appeared perfectly pristine, showing absolutely no evidence of any such activity. It presented as a lifeless, barren asteroid, yet it maneuvered with the distinct characteristics of an active comet. This contradiction begged for a solution, prompting the scientific world to put forth a series of hypotheses, each one more unconventional than the last. One proposal theorized that Oumuamua was a cosmic iceberg made of solid molecular hydrogen. The sublimation of this ice would generate thrust, but because hydrogen gas is transparent, the process would be completely invisible to our instruments. The chief issue with this idea is that solid hydrogen can only form at incredibly low temperatures, making it highly probable that such an object would have vaporized well before it ever reached our solar system. Another theory suggested it might be a fragment of nitrogen ice, sheared off from a distant, Pluto-like planet in another star system. The outgassing from sublimating nitrogen could also be invisible, but this explanation rests on a cascade of highly improbable assumptions. It was against this backdrop of confounding ideas that Avi Loeb presented his most audacious theory. What if the force propelling Oumuamua wasn't gas erupting from its interior, but the pressure of light pushing it from the outside? We often perceive sunlight as something without substance. Yet photons, the fundamental particles of light, possess momentum. When these particles impact a surface, they impart that momentum, creating a minuscule but relentless pressure known as radiation pressure. For dense, massive bodies like planets and asteroids, this force is utterly insignificant compared to the pull of gravity. However, for an object with an extremely large surface area and very little mass, like an incredibly thin sheet, radiation pressure can become the dominant force, capable of driving it through space. This is the fundamental principle behind a solar sail, and Loeb proposed that Oumuamua was precisely that, an artificial object, possibly less than a millimeter thick, engineered by an extraterrestrial civilization. This hypothesis elegantly resolved both of the object's major anomalies. First, a flat, sail-like shape would be optimal for catching light, and would explain the dramatic fluctuations in its brightness. Second, the pressure from sunlight provided a perfect explanation for its non-gravitational acceleration, without requiring any visible outgassing. Unfortunately, there was absolutely no way for us to verify this extraordinary claim, which brings us to the tragic dimension of Oumuamua's story. We spotted it far too late. The object was only detected after it had already passed its closest points to both the Sun and the Earth. It had approached us from the direction of the Sun, a region of the sky that astronomers deliberately avoid to protect their sensitive equipment. We only caught sight of it as it was on its way out, as if noticing a guest just as the door was shutting behind them. We were left with a fleeting window of just a few weeks to observe it, before it grew too dim and disappeared forever into the void of interstellar space. There was never any possibility of dispatching a spacecraft to get a closer look, leaving us with a cascade of unanswered questions. Was Oumuamua a natural object possessing a bizarre combination of properties never before witnessed? Or could Loeb have been correct, and we had just seen a brief flyby of an alien technological artifact? We don't have the answer, and in all likelihood, we never will. But its legacy is undeniable. It opened our eyes to the reality that interstellar space is not a void, and that objects fundamentally different from anything in our own solar system can journey through it. This event set a precedent, motivating astronomers around the globe to retune their instruments to scan for more cosmic visitors. Oumuamua acted as a scout that blazed a trail, and everyone eagerly awaited the arrival of the next interstellar messenger. Following the unsettling and perplexing enigma of Oumuamua, the scientific community held its breath in anticipation. Astronomers now understood that the first interstellar visitor was no mere fluke, but the dawn of a new age in cosmic exploration. It was only a matter of time before a second one appeared. What form would it take? Would it mirror the bizarre behavior of its predecessor, adding weight to the suspicions held by Loeb and his supporters? Or would it prove to be something more predictable and easily understood? The answer arrived 2 years later, in August of 2019. It came not from the automated systems of giant observatories, but from the sharp eye and relentless dedication of one individual, Comet Borisov, an amateur astronomer from Crimea. His is a story that truly merits its own focus. In an era where astronomy has become heavily industrialized, relying on massive, billion-dollar installations, Borisov represented a vanishing breed of classic comet hunters. He used a telescope of his own design, which he had literally constructed in his own garage. Night after night, he methodically swept the heavens, searching for new and undiscovered comets, and on one of those nights, his perseverance was rewarded. He detected a faint, fuzzy object that appeared on no existing star charts. Initially, it might have been mistaken for just another common comet originating within our solar system. But as Borisov and the astronomers he alerted began to calculate its trajectory, it became evident that this was something truly extraordinary. Much like Oumuamua, the new object followed a distinctly hyperbolic path, confirming it as the second interstellar visitor in recorded history. To honor its discoverer, the object was officially designated 2I/Borisov, though it soon became known simply as Comet Borisov. From the very beginning, this new visitor was the complete antithesis of Oumuamua. Where its predecessor was mysterious and confounding, Comet Borisov was comfortingly ordinary and behaved exactly as astronomers had always expected an interstellar wanderer would. First, there was its appearance. Unlike Oumuamua, which remained a sterile point of light, Comet Borisov immediately showed its cometary nature. Even through Borisov's own telescope, the object was clearly surrounded by a distinct coma,
a glowing cloud of gas and dust illuminated by the distant sun. As this visitor drew nearer to our star, it began to develop a clearly discernible tail, confirming its identity beyond any doubt. This new visitor acted precisely as a standard textbook comet would, coming to life right where expected, actively releasing gas and dust through sublimation, and making no effort to conceal it. There was no perplexing mystery of unexplained acceleration. Comet Borisov exhibited both the acceleration and the visible outgassing that was clearly causing it. Furthermore, its composition was telling. The emergence of a brilliant coma provided astronomers with a golden opportunity that had been absent with Oumuamua. The ability to analyze the chemical makeup of the material this interstellar guest was composed of. To do this, they employed a technique called spectroscopy, where the light from the comet's coma was directed through a spectrograph, an instrument that splits it into a spectrum, much like a rainbow. This resulting rainbow, however, was not a continuous band of color. It was interspersed with dark and bright lines, creating a kind of unique barcode. Since every chemical element and molecule possesses its own distinct barcode, scientists could use these lines to identify the exact gases present in the coma, and even determine their relative amounts. The spectrum of Comet Borisov offered no sensational surprises, a fact that was, in itself, a profoundly important discovery. Its coma was found to contain molecules such as cyanogen and diatomic carbon, compounds that are entirely typical for comets originating in our own solar system's Oort cloud. The proportions of these components were also strikingly similar to what we observe in our native comets. A more detailed analysis later revealed that Comet Borisov's coma had an unusually high concentration of carbon monoxide. This detail might suggest that it formed in an extremely cold part of its home star system, perhaps a great distance from its star. Yet even this characteristic wasn't unheard of, as we are aware of comets within our own system that display similar anomalies. This finding was incredibly significant, because Comet Borisov represented our very first chemical sample from another planetary system. What this sample demonstrated was that the same fundamental laws of chemistry and physics that govern our corner of the universe are also at play around other stars. The processes that form planets and comets appear to be universal across the galaxy, meaning other star systems are not alien mirror worlds but are, in fact, much like our own. Comet Borisov served as confirmation of this fundamental principle of universality. Thirdly, its trajectory was entirely predictable, obeying the laws of gravity with impeccable precision. There were no anomalous accelerations that couldn't be fully explained by natural outgassing processes, allowing its path through our solar system to be mapped and calculated from start to finish without any surprises in its celestial mechanics. In this way, Comet Borisov effectively became a control sample for scientists. It showed us what a typical interstellar wanderer should look and act like. A completely ordinary comet, distinguished only by its origin, having been ejected from its native system billions of years ago to drift through interstellar space until it happened upon us. Its discovery carried enormous weight. On one side, it tempered the enthusiasm for more radical hypotheses. Skeptics could now point and say that the second visitor was perfectly normal, suggesting Oumuamua was likely just a highly unusual but natural comet, whose properties we couldn't grasp due to insufficient data. Borisov seemed to steer the scientific conversation back toward a more calm and conservative track, championing Occam's razor. On the other side, the story of Comet Borisov only served to accentuate the strangeness of Oumuamua. Now you had a basis for comparison. If Borisov represented the norm, then Oumuamua was clearly the exception, its uniqueness becoming even more pronounced. This created two distinct poles, one an absolutely perplexing, asteroid-like object with baffling motion, and the other a completely understandable, classic comet.
While statistics based on just two examples are hardly definitive, they did raise a compelling question. Was it mere coincidence that the first object was so bizarre while the second was so predictable? Or could it indicate that interstellar space contains at least two entirely different classes of objects? It was within this context that our third visitor, designated 3I/CL, made its appearance. After the arrival of Comet Borisov, many assumed that any subsequent interstellar guests would follow its pattern and be normal comets. Reality, as it so often does, proved to be far more fascinating. This third traveler was unlike either the mysterious Oumuamua or the straightforward Comet Borisov. It was something else entirely, combining traits of both while introducing its own unique oddities. These new peculiarities were not related to its physical nature, but to the very geometry of its journey. Its orbit, the path it took through our cosmic neighborhood, looked as if it had been meticulously planned. You see, every object in the cosmos, from a speck of dust to an entire galaxy, writes its own autobiography in the language of its movement. An orbit is more than just a line on a star chart. It's a record of its past and a forecast of its future. An orbit reveals where an object was born, the gravitational forces it has encountered, and its ultimate destination. With object 3I/CL, this biography read as suspicious from the very beginning. Its trajectory felt too precise, too deliberate, as if it were authored not by the blind forces of chance, but by an intelligent choreographer directing a sophisticated celestial performance. To appreciate why this trajectory raised red flags, you must first picture the architecture of our solar system. Imagine it as a vintage vinyl record player. At the center is the sun, the spindle, and extending outward are the almost perfectly circular grooves that represent the orbits of the planets. The entire system is remarkably flat. Mercury, Venus, Earth, Mars, Jupiter, and the other planets all travel in more or less the same plane, which astronomers refer to as the ecliptic plane. While minor deviations exist, our system largely resembles a giant, flat disk. This structure is the enduring legacy of our collective birth from a swirling cloud of gas and dust. Picture yourself inside a vast, dark chamber with a record player spinning at its center. Imagine dust motes streaming toward it from every direction, the ceiling, the floor, and all the walls. This scene serves as an analogy for how interstellar objects are expected to enter our solar system. Because these objects originate from stars scattered randomly across the sky, there's no logical reason for their paths to align with the flat plane of our system's disk. Instead, they should intersect it at a wide variety of arbitrary angles. The first significant anomaly of 3I/CL's orbit emerges right here. Because its trajectory was inclined to the ecliptic plane by a mere 5 degrees. Rather than plunging into our system from above or below, as probability would suggest, it arrived on a path almost perfectly parallel to the rotating disk of our planets. Its approach gave the distinct impression that it was deliberately targeting this thin, densely populated slice of space, which is an extremely unlikely event for any random object. Let's consider just how improbable this is. While some cited calculations are a matter of debate, even conservative estimates place the likelihood at around 6%. Think of it as firing an arrow at a target. Just hitting the target's surface is a decent shot. However, 3I/CL appeared to be aiming not for the face of the target,
but for its incredibly thin edge. As Loeb and his colleagues noted in their paper, the chance of this happening is under 1%, making it a highly unusual occurrence. This stands as the first strange chapter in its story, a coincidence we should bear in mind as we continue. The second anomaly concerns its direction of travel. If you revisit our record player analogy, all the planets spin in the same direction, counterclockwise when viewed from above Earth's North Pole, a direct consequence of the primordial protoplanetary disk's rotation. Object 3I/C, however, does the precise opposite, moving in a clockwise or retrograde direction. It is flying directly against the established flow of celestial traffic in our solar system. From a purely statistical perspective, there's nothing especially strange about this. A random object has a 50-50 chance of traveling in either direction. The situation becomes far more compelling, however, when you analyze it through the principles of physics and potential objectives. By moving against the planetary current, 3I/C ensures that its relative speed during any close approach is maximized. It's akin to a head-on collision on a freeway, with the vehicle's speeds combined to create an incredibly energetic impact.
Under these high-speed conditions, any gravitational maneuver becomes significantly more pronounced and dynamic, presenting both immense opportunities and great risks for altering its path. This approach represents the most energy-intensive but also the most efficient method for interacting with the system's bodies. Had it traveled in the same direction as the planets, its encounters would have been slower and more gradual, like one car chasing another. The most intriguing part, however, arises when we analyze these two anomalies not in isolation but together. The probability of two independent events, both happening, is found by multiplying their individual probabilities. When you combine the very low chance of its near-perfect alignment with the ecliptic plane and the 50% chance of its retrograde motion, the overall likelihood of such a scenario remains remarkably small. Imagine a circular highway where all traffic flows counterclockwise. A car suddenly appears, but instead of using an on-ramp, it smashes through a barrier to enter the road almost perfectly parallel to the lanes, a highly improbable event in itself. Then, having achieved this, it immediately begins driving against the flow of traffic. While one could attribute this to a freak accident, any observer would naturally suspect that such actions were deliberate. This is the very suspicion that the orbit of 3I/C raises. Its behavior seems perfectly orchestrated for a specific purpose, to encounter the planets. Aligning with the ecliptic plane guarantees it will cross their orbital paths, while its retrograde motion ensures these encounters will be as effective as possible. This celestial choreography feels too deliberate, too meaningful. By contrast, Oumuamua also crossed the ecliptic, but did so at a steep angle, just as a random visitor would. It simply pierced our system and continued on its way, whereas 3I/C glides along the plane like a stone skipping on water, suggesting it came not just to pass through, but to engage. Of course, a skeptic would rightly point out our human predisposition for finding patterns in random data, a phenomenon known as apophenia. We perceive familiar shapes in clouds and constellations, and perhaps we are simply projecting intent onto a random cosmic trajectory. It is possible that we have just been fortunate enough to witness an exceedingly rare but entirely natural event. After all, among the billions of interstellar objects roaming the galaxy, it was statistically inevitable that one would eventually appear on this exact trajectory for us. Perhaps that time is now. While this explanation is logical and cautious, it doesn't dismiss the extraordinary possibilities presented by 3I/C's orbit.
These are opportunities that would be unavailable to a random piece of rock, but which an intelligent probe could readily exploit. The potential for a sequence of gravitational maneuvers, allowing it not just to pass through but to remain in our system, transforms this story from a series of curious coincidences into a gripping scientific thriller.
If you consider 3IC's trajectory to be a musical score, then the gravity of our planets is the orchestra poised to perform it. The resulting symphony would sound like a powerful anthem dedicated to a sophisticated intelligence. The journey ahead for this visitor isn't just a simple inertial flight. It's a series of complex pirouettes that in astronautics are known as gravitational assists.
This art of using a planet's gravity to manipulate speed and direction is not the stuff of science fiction. It has been a standard tool for engineers at NASA, Roscosmos, and other space agencies for over half a century. To understand the principle of this gravitational surfing, you don't need to be an expert in celestial mechanics. Imagine you're on a skateboard, moving at a steady speed on a flat road when a large truck overtakes you. If you reach out at the right moment and grab onto its side, it will pull you forward, giving you a major boost. And when you let go, your speed will be substantially higher. You will have effectively borrowed some energy from the truck. In space, the role of that truck is played by massive planets, and their gravitational fields act as your extended hand. When a spacecraft passes a planet, it dips into its gravitational well, which accelerates the craft and bends its path. Should the spacecraft approach from behind a planet, moving with its orbit, the planet will essentially grab it and fling it forward, increasing its velocity. This is the classic gravitational slingshot effect. Conversely, if a spacecraft meets a planet head-on, it gives up some of its own momentum, causing it to slow down. This brilliant maneuver allows for massive savings in fuel, which is the most precious and strictly limited resource in space exploration. Without the help of gravity assists, many of our most renowned interplanetary missions would simply have been impossible. The legendary Voyager 1 and Voyager 2 probes, launched in 1977, are the most dramatic example of this technique in action. Their mission, known as the Grand Tour, was only possible because of a special planetary alignment that occurs just once every 176 years. The Voyager spacecraft used Jupiter's gravity to slingshot toward Saturn, then Saturn's gravity to propel them toward Uranus, and finally, Uranus's gravity to reach Neptune. They leaped between planets like cosmic surfers, riding one gravitational wave after another, a technique that reduced the journey time to Neptune from 40 years to a mere 12. Gravitational assists are not limited to acceleration. They are also highly effective for deceleration. A perfect contemporary case is the Parker Solar Probe, which has a mission to fly closer to the Sun than any craft in history to study its corona. To enter such a tight solar orbit, a probe launched from Earth must first eliminate our planet's staggering orbital velocity of almost 30 kilometers per second. This feat is impossible with rocket engines alone, as no spacecraft could carry enough fuel. Instead, engineers developed an elegant plan. The Parker probe conducts multiple flybys of Venus. Each time it passes in front of the planet, it offloads some of its energy, which causes its orbit to shrink and pulls it progressively closer to the Sun. In essence, it uses Venus as a gravitational brake. Now, equipped with this knowledge, let's analyze the potential flight path of Object 3I/C, which seems to follow a pre-written script for an interplanetary mission. The first act starred Jupiter. The object has already passed the most massive gravitational truck in our system, which, even from a distance, could have finely tuned the visitor's trajectory, setting the stage for what would follow. The second act is set at Mars. The object's next major encounter will be with the red planet, and it's projected to be so close that astronomers are hopeful our orbiting probes there will be able to capture an image. This would provide us with our very first look at the mysterious visitor. From a celestial mechanics standpoint, the Mars flyby offers another crucial window to adjust its course. This brings us to the third act, the critical hypothetical maneuver, where the story becomes truly fascinating. Calculations by Avi Loeb and his team suggest that if 3I/C is a controlled object, it would only need to execute a tiny, almost imperceptible engine burn as it passes Mars. This small thrust would place it on a trajectory to use the gravity of either Mars or later Earth for one final, decisive maneuver. The finale of this performance, according to these calculations, would send the object directly toward Venus. And as we know from the Parker Solar Probe, a Venus flyby is the perfect method for braking. By performing such a maneuver, 3I/C could shed its excess interstellar velocity, allowing it to be captured by the Sun's gravity and shift into a stable, elliptical orbit. It would no longer be a temporary guest, but could become a permanent resident of the solar system. This precise sequence of encounters, Jupiter, Mars, and Venus, is an exceedingly rare possibility for a random object just passing through. The fact that this exact chain of events could also create the perfect scenario for the object's capture into our system pushes the limits of what one might attribute to mere coincidence. The object's behavior suggests a meticulously crafted strategy, much like one we would devise to send a probe to a new star with the intent of conducting thorough research and establishing a stable orbit. Of course, this is merely a speculative but calculated scenario. Should 3I/C prove to be nothing more than a lifeless chunk of rock and ice, it will forego this opportunity, adhering to a predictable gravitational arc past Mars and continuing along a hyperbolic path that will carry it away from us forever. However, the conclusive proof, the smoking gun, would be any detectable deviation from this calculated trajectory. If, following its flyby of Mars, the object adjusts its course by even a minuscule fraction of a degree or alters its velocity in a way that defies Newtonian physics, it would be almost irrefutable evidence. Such an event would strongly indicate that the object is not drifting blindly, but is under powered, guided control, following an intentional path rather than an accidental one. We are in a unique position to witness this history unfold in real time. Over the next few months, astronomers across the globe will intently monitor every detail of its movement, searching for that tiny, anomalous impulse that could change everything we know. If such a propulsive signature is confirmed, the primary question for humanity will transform from a scientific one to a philosophical, and perhaps unsettling one. What is its reason for wanting to stay here? As we seriously contemplate the hypothesis that object 3I/C is a controlled probe and not a natural body, we move beyond the familiar domains of astronomy and celestial mechanics. We venture into a territory governed not by precise formulas, but by grand and often troubling philosophical concepts. The question of its composition is quickly superseded by the question of its purpose, and to even attempt an answer, you must confront two of the most significant intellectual puzzles in the search for extraterrestrial intelligence: the Fermi paradox and the dark forest hypothesis. Let's begin with the first. The Fermi paradox stems from a famous question that physicist Enrico Fermi is said to have posed to his colleagues during a lunch in 1950. It seems deceptively simple. Where is everybody? The logic behind this question is both flawless and inescapable. Our Milky Way galaxy is vast, containing, by the most conservative estimates, between 100 billion and 400 billion stars. Data from observatories like the Kepler Space Telescope confirm that planets are the rule, not the exception, with nearly every star hosting its own system, and billions of these worlds exist in the habitable zone, where liquid water is possible. Furthermore, our galaxy is ancient, at roughly 13.5 billion years old, while our own solar system formed only 4.5 billion years ago. This means that for eons, on billions of planets, life, much like our own, could have arisen and evolved into intelligent civilizations long before humans ever appeared. If you assume that even a tiny percentage of these civilizations developed technology for interstellar travel, mathematics suggests they should have colonized or at least explored every corner of the galaxy by now, leaving behind colossal structures, radio signals, or other artifacts.
And yet, we observe nothing. Space appears to be empty, the radio spectrum is silent, and the sky offers no signals. This is the heart of the paradox. The stark discrepancy between the high theoretical probability of alien civilizations and the complete absence of any observable evidence for their existence. Over the decades, numerous potential solutions have been proposed, from the rare Earth hypothesis, suggesting we are a cosmic fluke, to the Great Filter hypothesis, which posits that civilizations inevitably destroy themselves.
Another idea, the zoo hypothesis, suggests advanced beings are deliberately hiding from us. Within this context of profound cosmic silence, the arrival of object 3I/C, if you entertain the idea of its artificial nature, feels like the first coherent whisper in a deafening void. It doesn't solve the Fermi paradox, but it might hint at which solution is correct. This is where the second, far more ominous concept comes into play, the dark forest hypothesis, popularized by science fiction author Liu Cixin in his novel The Three-Body Problem. Remarkably, this is a rare case where science fiction so accurately reflects a scientific debate that it has become a key part of the conversation. The novel is even cited directly in the academic paper by Loeb and his colleagues. The dark forest hypothesis offers one of the most terrifying, yet logically coherent, solutions to the Fermi paradox. It argues that the universe is not empty, but is teeming with life. This life, however, remains silent not due to a lack of technology or curiosity, but out of absolute, primal fear.
To grasp the concept, imagine a vast, dark forest at night, filled with countless hidden hunters. Each hunter is a separate civilization, driven by the core instinct to survive, but completely unaware of the intentions of any other. If one hunter becomes aware of another, the most dangerous possible move is to call out and reveal its own position. With no way of knowing if the other is friendly or hostile, the safest and most logical course of action is to remain silent, and possibly to eliminate the other before it can become a threat. They can never be sure that their language and motives will be interpreted correctly. Since any detected civilization creates an existential risk, the one that attacks first secures an undeniable upper hand. Consequently, the only viable strategy for survival in this dark forest is to maintain silence, to stay hidden, and to eliminate any other presence that foolishly discloses its position. The universe appears silent because any civilization that made noise was eradicated long ago. This idea completely inverts the logic behind the Search for Extraterrestrial Intelligence, or SETI, program. From this perspective, our efforts to broadcast radio signals into space are not warm invitations, but rather careless shouts in a wilderness teeming with hunters. Now, let's consider object 3I/C through the framework of this unsettling hypothesis. If this object is indeed an artificial probe, what principles guide its actions, and what is its purpose here in our cosmic forest?
we can imagine at least two potential scenarios playing out. The first possibility is that we are dealing with a reconnaissance probe, which represents the more optimistic outlook. The civilization that dispatched this probe operates by the rules of the dark forest, refraining from broadcasting its own existence across the galaxy. Instead, it sends out countless small, silent, and unobtrusive scout probes, whose primary mission is to passively collect information. To avoid detection not only by us, but more critically by other, more dangerous predators, such a probe would need to mimic a natural object flawlessly. Its disguise as a comet serves as ideal camouflage, allowing it to approach a world with life-bearing potential, analyze its atmospheric and technological signatures, gauge our level of development, and then depart silently to transmit its findings back to its creators. This kind of visit isn't an overture for contact. It is an act of galactic espionage.
The second scenario, that of a cleaner probe, is a significantly grimmer interpretation, derived directly from the dark forest's brutal logic. If the ultimate survival strategy involves wiping out all potential rivals, then advanced civilizations might have developed an automated planetary defense system. They could have launched self-replicating killer probes in every direction, programmed with a simple directive. Find a planet where a technological society is emerging and execute a preemptive strike, destroying it in its infancy before it can pose a future threat. Under this interpretation, 3I/C is not a scout, but a weapon, and its complex trajectory is not designed for exploration, but for positioning itself optimally for an attack, or for prolonged surveillance before it strikes. Both of these hypotheses are, of course, entirely speculative, yet they effectively demonstrate the incredibly high stakes of this cosmic game. Observing object 3I/C is not just about satisfying scientific curiosity. In the most extreme, though logically plausible scenario, it could be a question of our species' very survival. There is, however, a third and more optimistic possibility that moves beyond the dark forest paradigm entirely. Perhaps the probe's creators are not hunters but explorers, much like us. Maybe it comes from a civilization that has transcended fear and is searching not for enemies but for allies. In that case, its arrival is not a menace, but the most profound gift in all of human history. A chance to make contact, to access new realms of knowledge, and to finally know that we are not alone. But the truth is, we have no way of knowing, and therein lies both the terror and the magnificence of this moment. We are standing at a precipice where object 3I/C, whether a simple rock or a sophisticated ship, forces us to confront this philosophical mirror. It makes us grapple with the most fundamental questions about our role in the cosmos, and as it continues its silent passage through our solar system, we are given time to reflect. Before we get lost in these metaphysical considerations, however, we have to return to solid scientific principles and pose the most critical question of all. Isn't it possible that a simple, ordinary, and entirely natural explanation exists for all these anomalies? Aren't we just fooling ourselves, building elaborate theories upon an incredibly unstable foundation? After such a dizzying exploration of extraterrestrial psychology and complex galactic espionage scenarios, it is easy to lose our analytical footing. Our imagination, sparked by an incredible series of coincidences, is primed to perceive deliberate intent in every shadow. It is precisely at moments like these that science requires us to step back, take a breath,
and employ our most effective weapon against self-delusion, Occam's razor. This philosophical principle, first articulated in the 14th century by the English friar William of Ockham, posits that one should not multiply entities without necessity. In contemporary language, this means that when you have two theories that explain a phenomenon equally well, you should opt for the simpler one, the one that relies on the fewest new assumptions. If a knocking sound in your wall could be caused by the plumbing, you should not immediately leap to the conclusion that it's a ghost. You must check the pipes first. Science is inherently conservative. It will always favor the known over the unknown. Therefore, before we can declare object 3I/C to be an artificial probe, the scientific method demands that we exhaust every possible attempt to explain its peculiarities using the natural laws we already understand. This is the part where the devil's advocate, or in this instance, nature's advocate, gets to speak. It involves the necessary, if less thrilling, work of checking all the pipes in our system before we start talking about ghosts. Let's start with the first anomaly, its early activity near Jupiter's orbit, which at first appears to be the most compelling piece of evidence for the object's unique nature. We initially assumed that for a comet to become so active in such cold conditions, it must be composed of highly volatile substances, like frozen carbon monoxide or nitrogen. But when we ask how likely that is, the answer turns out to be far more plausible than you might first think. Our entire understanding of what comets are made of is derived from studying those within our own solar system, which represents just one of countless cosmic possibilities. Our Sun is classified as a yellow dwarf, yet the galaxy's most prevalent stars are red dwarfs, considerably smaller and cooler. Planetary systems orbiting these stars would develop under vastly different temperature gradients. The snow line in such a system would be situated much nearer to its star, meaning the primary materials for comets in the frigid outer reaches might be frozen nitrogen or methane, not the water ice we are familiar with. This suggests that if 3I/C originated from a red dwarf system, its composition, while unusual to us, could be entirely standard for its place of origin. Its early sublimation might not be a sign of uniqueness, but simply its reaction to the exceptionally warm environment of our solar system. For such an object, the region near Jupiter would feel almost tropical. Furthermore, even comets we consider ordinary are not monolithic. Their nuclei can contain pockets of compressed gas that, upon heating, can burst explosively, generating a transient but brilliant coma long before the overall temperature is high enough for continuous sublimation. It's conceivable that what we observed was just such a random event. Regarding this second anomaly, its low orbital inclination, a probability of 5% or even 1% may sound exceptionally low. However, in the vastness of the cosmos, events with very low probabilities happen all the time. Here, we face a significant distortion in our perception, known as observer bias. Our telescopes are designed to scan the sky primarily along the plane of the ecliptic, because that is the region where the objects of greatest interest to us, the planets, asteroids, and comets of our own system, reside. We have effectively cast our nets in this specific area. Consequently, we are statistically far more likely to detect an interstellar visitor traveling within this plane than one passing high above or far below it. It's entirely possible that hundreds of interstellar objects are traversing our system at extreme angles, but they remain unseen because they are too faint and distant from our main search zones. What's more, our conclusions are based on a mere 3 observed objects, a sample size so small it is statistically meaningless. This is akin to flipping a coin 3 times, getting heads on each toss, and then declaring the coin must be double-headed, a conclusion any statistician would find ludicrous. To make any meaningful claims about the orbital distribution of interstellar objects, we would need to detect not 3, but several hundred, or ideally, several thousand. Only with such a robust dataset could we ascertain whether the low inclination of 3I/C's orbit is truly an anomaly or just a statistical fluke. As for the third anomaly, retrograde motion, we have already determined it is not an anomaly in any sense. The probability is 50-50, leaving no room for debate. The fourth anomaly, involving the potential for gravitational maneuvers, initially appears to be the most convincing argument for an artificial origin. Yet even here, the principle of Occam's razor proves devastating. This line of reasoning is a textbook case of post hoc rationalization, which involves fitting the data to a preconceived theory. As rational beings who design intricate plans and utilize gravitational assists for our own spacecraft, we instinctively project our own modes of thinking onto the universe. When we observe a trajectory that permits such complex maneuvers, we unconsciously see intention where there may be none. The mere existence of a potential pathway is not evidence of its deliberate use. Imagine you are hiking on a mountain and discover a rock formation that looks almost exactly like an armchair. Would you conclude that ancient giants carved it for their comfort? Of course not. You would recognize it as a random product of geological erosion. We perceive a chair because our brains are hardwired to identify familiar patterns. In the same way, we see mission scenarios in the flight path of 3I/C because we are familiar with the concept of space exploration. The solar system is an intricate three-dimensional web of gravitational fields, and any object passing through it will inevitably have its trajectory altered by planets. Among the infinite possible paths, some will, by pure coincidence, resemble a purposeful route. What we are likely observing is not a premeditated plan, but a fluke of celestial geometry, until we witness an actual physical deviation from its predicted course, the firing of an engine. Any discussion of maneuvers is nothing more than sophisticated mathematical speculation. At this point, someone playing devil's advocate might argue that while each anomaly can be explained away individually, the probability of all these highly unusual events converging on a single object is itself compelling evidence. This is a fair and powerful point, and it's what makes this whole debate so fascinating. This conflict highlights a fundamental clash between two scientific philosophies. The conservative method requires us to examine each piece of evidence in isolation, and, if a natural explanation is plausible, to accept it. A more radical approach, like the one taken by Avi Loeb, urges us to view the evidence holistically, arguing that the combination points to something extraordinary. But even when considering the whole picture, Occam's razor advises caution. We are still dealing with an object about which we know astonishingly little. Its precise size, shape, composition, and rotational speed are all mysteries. We are constructing grand hypotheses on a weak foundation of a few faint pixels from a CCD sensor. The most straightforward and economical explanation for this collection of oddities is not the arrival of an alien probe, but the realization that the universe is far more diverse and strange than we currently imagine. The object known as 3I/CATL is most likely not an artifact, but rather a profound and invaluable lesson, reminding us just how much we still have to learn. This experience teaches us that our assumptions about the nature of comets, formed by observing a very small segment of our galaxy, might be surprisingly simplistic and flawed. From a position of rigorous scientific skepticism, the idea that the object has a natural origin must therefore remain our primary and most likely working theory. The responsibility falls on those who propose an alternative to furnish compelling evidence. They need to provide not just circumstantial details or improbable coincidences, but direct and undeniable proof of artificiality, such as a documented maneuver, a spectral analysis revealing industrial metals in its coma, or even a radio signal.
Until such proof emerges, we have to stay grounded in known science. However, even with our feet firmly planted, we can entertain a particularly clever objection. What if this entity is aware of the principle of Occam's razor? What if it is intentionally conducting itself in a manner that keeps us guessing, compelling us to seek natural causes right up to the very end? This raises the question of whether we are observing a mere object or a true master of deception. Just when the arguments for a natural explanation appear almost unassailable, and Occam's razor has trimmed away all speculative theories, the discussion could easily conclude. We might simply decide that 3I/C is an exceptionally bizarre comet and close the case, awaiting the next cosmic visitor. But it is at this very point that a truly intriguing and almost spy-like concept enters the intellectual arena. What if we are looking at an artificial object that is merely masquerading as a comet? What if all our observations, the coma, the tail, and the unusual activity, are not natural phenomena, but part of an intentional camouflage, a smokescreen crafted to hide its actual identity? This single thought elevates our entire investigation to a new plane. We shift from being passive observers of physical events to active participants, trying to decode an alien strategy, suspecting we are confronting not just an anomaly, but a calculated deception. This is no longer a matter of physics, it is cosmic-scale game theory. Let's explore this hypothesis further. Why would an incredibly advanced civilization, after sending a probe to another star system, go to such lengths to disguise it? The motivations could be both profound and complex, leading us back to the dark forest philosophy, but approached from a more pragmatic angle. The first reason might be a principle of non-interference. Picture a civilization not of aggressors, but of researchers, galactic anthropologists. Their guiding principle could be similar to Star Trek's Prime Directive: avoid meddling in the organic evolution of less developed societies. For a culture at our stage, direct contact could trigger devastating outcomes like cultural shock, religious turmoil, and societal breakdown, as we struggle to accept we are neither alone nor the pinnacle of creation. To study us without inflicting such damage, their probe would need to be utterly inconspicuous, behaving like a biologist watching timid wildlife from a carefully concealed blind. And what could serve as a better disguise in the vastness of space than one of the most ordinary and chaotic of celestial objects, a comet? No one would ever suspect a simple comet of conducting espionage. It is the perfect cover. The second reason, however, involves the even more serious paradigm of the dark forest and safety. Perhaps the probe is not hiding from you and me. At our current technological level, we are no danger to it. Instead, it might be concealing itself from other, vastly more powerful hunters who could be silently patrolling the galaxy. Remember the logic of the dark forest. Any object that exhibits clear signs of technology, such as active engines, an unnatural spectrum, or radio signals, immediately becomes a potential target. In such a dangerous universe, disguising itself as a natural object is more than a tactic. It is a core survival strategy. The probe would masquerade as a comet for the same reason a soldier on a battlefield wears camouflage instead of a brightly colored uniform, to avoid being seen by a sniper. And in this scenario, we might find ourselves unwittingly positioned in the line of fire between this scout and some hypothetical observer. If you accept this line of reasoning,
The entire collection of oddities surrounding object 3I/C takes on a completely new meaning. It transforms from a sequence of unrelated anomalies into a meticulously engineered system of camouflage. Let's speculate, within scientific bounds, on how such a cometary simulation could be achieved. The probe itself could be a relatively compact, solid device carrying reservoirs of liquefied or compressed gas, like neon, argon, or xenon. As it nears our solar system, its automated systems would begin to release this gas into space, which would then expand in the vacuum to form an artificial coma enveloping the craft, making it appear brighter and more diffuse, just like a real comet. Along with the gas, the probe could also disperse a fine dust made of silicate or carbon nanoparticles. These particles, pushed by the pressure of solar radiation, would create a synthetic dust tail. This would not only complete the disguise, but also cleverly obscure the true spectral signature of the probe's body. The light we would be analyzing would be the reflection from this artificial dust cloud, not from the metallic surface of the device itself. Such a system could also perfectly replicate erratic activity. The probe could time the activation of its coma to begin near Jupiter's orbit, catching our attention while appearing as a rare but natural event, and could vary the intensity of its gas release to simulate the geysers and flares seen on actual comets. While this concept of cosmic mimicry seems drawn from science fiction, it possesses a critical advantage. It remains within the realm of what we can potentially verify.
When we suspect we're facing not a natural phenomenon, but a deliberate deception, we can look for its potential flaws. So, how might you unmask such a cosmic disguise? The first method involves ultra-detailed spectroscopy. Even if a probe were to generate an artificial coma, its chemical makeup could give it away. For instance, if a spectral analysis detected gases that are never found in such high concentrations in natural comets, like inert gases, or if we could analyze the material's isotopic composition. Isotopes are just versions of a chemical element with different atomic masses, and the ratio of isotopes like deuterium to hydrogen in our solar system creates a kind of local signature. If the isotopic fingerprint of the gases in 3IC's coma starkly contrasts with our own, that would be powerful evidence of an extraterrestrial origin, and discovering isotopes that could only be formed through artificial nuclear reactions, perhaps from a probe's engine, would amount to direct proof. A second approach is to analyze the dynamics of the coma and its tail. A natural coma expands and dissipates based on the established laws of gas dynamics and gravity, with dust particles in its tail following precisely defined Keplerian orbits. Should we be observing an artificial emission, these dynamics could be noticeably different. For example, the outgassing might start and stop with an abruptness that doesn't correspond to changes in its distance from the sun. Alternatively, we might observe that particles in the tail behave unusually. Perhaps they are all of a uniform size, which is uncharacteristic of natural fragmentation, or their trajectories suggest they were ejected with a specific initial velocity. While this would demand extremely precise and sustained observation, it is certainly feasible. The third method is a hunt for thermal anomalies. Any sophisticated technology, from engines and computers to communication systems, radiates heat, leaving a distinct thermal signature. By pointing a powerful infrared instrument, like the James Webb Space Telescope, at the object, we could search for excess thermal radiation that can't be explained by solar heating alone. If the object is warmer than a simple chunk of ice should be at that distance, it would imply an internal power source is active within it. This entire hypothesis of cosmic camouflage transforms our role from that of passive observers to something more akin to active counterintelligence agents. We would no longer be merely searching for anomalies, but for indications of intentional concealment, for the seams in the disguise. This presents an extraordinarily difficult challenge, one that pushes the very boundaries of our technological abilities. Yet the concept itself is transformative. It suggests that the absence of obvious signs of artificiality does not confirm a natural origin. It could simply mean that we have not yet learned how to scrutinize things closely enough. And this very notion of searching for hidden artifacts leads us back to Avi Loeb, as he has already taken this idea to its next stage. He has transitioned from observing distant phenomena to actively seeking their physical evidence right here on Earth. His expedition to the ocean floor represents the first real attempt at this kind of cosmic archaeology, a quest for fragments of another world buried at the bottom of our own. While the scientific community was caught up in debates over distant faint points of light like Oumuamua and 3I/C, Loeb posed a question that both broadened and focused the search. What if we don't have to gaze into the vastness of space, hoping to catch another fleeting visitor? What if remnants of interstellar travelers are already here, right under our noses, on our own planet? What if some didn't just pass by, but actually fell to Earth, and all we need to do is figure out how to find them? This line of thinking, a logical extension of his cosmic archaeology philosophy, spurred one of the most unconventional and ambitious scientific expeditions of our time. The journey began in archival records. Loeb and his student Amer Siraj undertook a re-examination of catalogues documenting bolides, which are exceptionally bright meteors, captured by a satellite network managed by the U.S. Department of Defense. These satellites, initially intended to track ballistic missile launches, are constantly monitoring Earth's atmosphere, recording any brilliant flashes with incredible precision. While sifting through years of this data, they discovered an event from January 8, 2014. On that date, a meteor detonated in the atmosphere over the Pacific Ocean, close to the coast of Papua New Guinea. On the surface, it appeared to be a routine occurrence, as tons of cosmic debris enter our atmosphere every day. However, the data for this particular meteor, which was designated IM1 for Interstellar Meteor 1, was truly exceptional. First, its velocity before hitting the atmosphere was immense, approximately 60 kilometers per second relative to the Sun. This speed was well beyond the solar system's escape velocity, offering a clear and unambiguous indication of its interstellar origin. This made it the first interstellar meteor ever catalogued, predating the identification of Oumuamua by 3 years. But a second detail emerged that was even more compelling. By analyzing the altitude and brilliance of the explosion, it was possible to infer the strength of the object's constituent material. The calculations revealed that IM1's material was unusually robust. It survived far greater atmospheric pressures during entry than ordinary stone or even iron meteorites. It proved tougher than all 273 meteorites in the NASA catalogue for which comparable data existed. It was composed of something harder than iron. This revelation captivated Loeb's imagination. An interstellar object exhibiting anomalous material strength. What could it possibly be? Was it a natural metal alloy forged in the core of an exotic exploded planet? Or was it something artificial, like an alloy from a superior technology? To resolve this question, he had to find fragments of the meteor. The task seemed insurmountable. Searching for microscopic particles on the ocean floor at a depth of 15 kilometers and nearly a decade after they landed is like trying to find a needle not just in a haystack, but across an entire field. Nevertheless, Loeb remained undeterred. He initiated a crowdfunding effort, secured $1.5 million from private backers, and launched an expedition as part of his Galileo project.
In the summer of 2023, he chartered a state-of-the-art research ship and traveled to the precise location in the Pacific Ocean where calculations indicated the fragments of IM-1 should have landed.
The expedition's primary instrument was a form of magnetic dredge, which involved dragging powerful magnets along the ocean floor. The principle was straightforward. If the meteoroid contained iron or other magnetic elements, the molten droplets from its atmospheric explosion would cling to the magnets as they passed over the seabed. For weeks on end, the team methodically swept the ocean bottom, continuously hoisting the dredge to inspect everything it had collected. Their diligence was rewarded when they began discovering tiny, nearly invisible metallic spheres mixed in with volcanic sand and marine debris. These spherules, measuring just a fraction of a millimeter in diameter, are a well-known result of ablation, the process where a meteorite melts and sheds its surface as fiery droplets that cool into perfect spheres. The team ultimately gathered over 700 of these spherules, but this discovery led to the most critical question. Were these tiny spheres the actual remnants of the interstellar traveler, or were they merely common terrestrial contaminants like rust from old ships, industrial pollution, or even micrometeorites from within our own solar system? After returning to Harvard, Loeb and his colleagues commenced a meticulous analysis of the samples using highly sensitive mass spectrometers. The results, which they published in the scientific journal, were described as nothing short of extraordinary. The chemical makeup of some spherules was entirely different from anything found on Earth or in any previously studied meteorites.
These samples displayed a distinctive ratio of heavy elements, which Loeb designated as the B-La-U signature, derived from the symbols for beryllium, lanthanum, and uranium. The concentrations of these elements were hundreds of times greater than those found in meteorites originating from our solar system. For Loeb, this was the conclusive evidence he sought, the so-called smoking gun. He argues that such a peculiar chemical composition points not only to an extraterrestrial source, but to an extrasolar one, potentially from a planetary system that formed under vastly different chemical circumstances. Furthermore, the object's unusual initial strength, paired with this exotic composition, raises the possibility that it was an artificial alloy rather than a natural rock. Beryllium, for instance, is a key component in the aerospace industry for creating exceptionally strong and lightweight materials. Unsurprisingly, the scientific community met these claims with significant skepticism. Many meteorite specialists argued that drawing such sweeping conclusions from the analysis of microscopic spheres was premature. They proposed that the spherule's composition might have been altered by chemical interactions with seawater during their long stay on the ocean floor. Other critics pointed out that the search area was near the location of past American nuclear tests, suggesting the strange uranium enrichment could be a form of man-made contamination. Another possibility raised was that volcanic ash in the region could naturally contain high concentrations of certain elements. The debate is still ongoing, but whatever the final conclusion, Loeb's expedition has already secured its place in history.
This was humanity's first deliberate mission to locate and retrieve a physical sample of material from another star system. It represents a courageous shift from the passive observation of astronomy to the active fieldwork of what he has often termed cosmic archaeology. And Loeb hasn't stopped. He is already organizing new expeditions to gather more material, hoping to find larger fragments of IM-1. His journey across the ocean is a powerful testament to his unwavering commitment to his ideas. He is not content to simply theorize from his office. He is prepared to travel to the furthest corners of the globe and descend to the ocean's depths to collect evidence, piece by painstaking piece. This entire story
which is developing alongside our observation of the object known as 3I/c, creates a remarkable backdrop. On one side, we are using telescopes to probe the mysteries of an object hundreds of millions of kilometers away. On the other, we are sifting through sand on the ocean floor, searching for traces of its predecessor that arrived here nearly a decade ago. These two efforts are fundamentally part of a single, grand endeavor: the search for an answer to one of the greatest questions of all. As we navigate this maze of anomalies, daring theories, and skeptical objections, even diving to the seabed for clues from the past, we are brought back to the present moment. We return our focus to that silent point of light making its steady journey through our solar system. For us, the object 3I/c is no longer a simple astronomical code. It has become the vessel for all our hopes, our anxieties, and our immense scientific curiosity. What started as a simple data entry from a robotic telescope has evolved into a high-stakes drama that we are privileged to witness as it unfolds. Let's pull together all the threads of this complex situation for a clearer picture. We are observing an object that originated from outside our solar system. It has exhibited activity far earlier than expected, a behavior that is hard to explain without assuming it possesses either an enormous size or a highly unusual chemical structure. It follows an incredibly unlikely orbital path, moving in the opposite direction of the planets but almost perfectly aligned with their plane, which seems like an ideal trajectory for surveying our system. This unique path presents the opportunity for the object to execute a series of gravitational maneuvers. Such maneuvers could potentially slow it down enough for it to be captured by our system's gravity, allowing it to remain here indefinitely. The entire context for this event is shaped by its predecessors, the profoundly mysterious Oumuamua, which bolstered the idea of alien artifacts, and the reassuringly conventional Comet Borisov, our baseline for a natural object. So, what is different this time? Unlike Oumuamua, which we spotted far too late, object 3I/c was detected during its approach. This gives us the invaluable resources of time and the chance to prepare for its arrival. Humanity is poised to bring the full might of modern astronomy to bear on this visitor, aiming to extract every possible piece of information from its flyby. In the months ahead, particularly as it draws closer to the inner solar system, you should anticipate nothing less than a comprehensive scientific mobilization. The first and most vital task will be high-precision astrometry, the meticulous measurement of its position in space. A global network of dozens of telescopes, both ground-based and orbital, will track the object's celestial coordinates with unparalleled accuracy. This stream of data will converge at a single center where computer models will perpetually refine its trajectory. The ultimate goal is to contrast the object's actual flight path with a pure gravitational model, because any deviation that cannot be attributed to natural outgassing will serve as a definitive red flag, the very proof of engine activity that Avi Loeb has been searching for. The second major strategy involves detailed spectroscopy. As the object nears the sun, its coma, if it has one, will brighten significantly, allowing observation by the most powerful spectrographs at major observatory facilities like the Very Large Telescope in Chile or the Keck Observatory in Hawaii. Scientists will strive to not only identify its chemical composition, but also to measure its isotopic ratios, hunting for any chemical fingerprints in the gas and dust that might betray an artificial origin. A third method will be direct observation, with hopes that our Mars-orbiting spacecraft might capture images of the object during its close pass. Even poor-quality photos could prove invaluable, giving us a general sense of its shape and whether it is elongated like Oumuamua or has a more standard, irregular form. If we are fortunate, the James Webb Space Telescope could also contribute, as its extraordinary infrared sensitivity represents our greatest chance to detect a thermal anomaly indicative of an active internal power source. Much like any great thriller, this story has a deadline. Calculations show the pivotal events are expected to happen at the close of this year, with late November and early December being the critical period. This is the window when, according to Loeb's hypothesis, the object would need to make decisive maneuvers for a planetary encounter or orbital insertion. From here, two entirely separate futures could unfold before us. In the first scenario, the simplest explanation holds true. Object 3I/c is confirmed to be precisely what it appears to be: an exceptionally large and unusual, yet entirely natural comet. It will adhere strictly to its predicted gravitational course with no detectable maneuvers, and its spectrum, though strange, will reveal nothing overtly artificial. And here lies a bitter irony. Just as the object reaches its peak activity near the Sun, making it most interesting to study, Earth will be on the opposite side. Our own star will obscure our view, causing us to miss the most crucial moments as 3I/c vanishes back into interstellar space, leaving us with even more unanswered questions. In the second scenario, the unbelievable becomes reality. The outcome almost no one anticipates, but everyone secretly desires. Astrometry detects a small but statistically significant deviation. The object alters its course. Such a discovery would be the most momentous in human history, drawing a sharp line between a before and an after. News of this would cascade across the planet, triggering a storm of elation, fear, hope, and panic, and instantly making all debates on the Fermi paradox academic no longer. We would be faced with a functioning alien artifact right here in our solar system. The question that would then confront all of humanity would shift from scientific to political and existential. What should we do next? Do we try to make contact, prepare a defense, or simply stay silent in the hope that we haven't been noticed? We find ourselves standing on a threshold. Beyond it may lie a routine but important discovery about the diversity of comets, or it could be something so unimaginable that it forever redefines our understanding of ourselves. Regardless of the outcome, the story of 3I/c has already transformed us. This event has moved the most audacious questions from the fringes of science into the halls of prestigious academic institutions, compelling us to seriously debate the possibility of contact with rigorous calculations and observational plans. It has revealed the incredible power of our tools, capable of tracking a tiny speck arriving from another star. Above all, it demonstrates how science itself progresses through the collision of ideas, the boldness of some and the skepticism of others, and the slow, meticulous accumulation of facts. This global scientific investigation you are witnessing is, in itself, an answer to many questions, for it shows us exactly who we are. As a civilization, we had only just learned to walk upon our world when we immediately lifted our gaze to the stars. We are a species fundamentally driven by a need to solve every mystery, which is why we observe a faint point of light in the darkness not with fear, but with an unquenchable sense of wonder. It's possible that this single trait, our endless thirst for knowledge, is the most significant marker of intelligence anywhere in the cosmos. We persist in asking questions, fully certain that, one way or another, answers are waiting for us.